we enter into our fourth lecture, I want to point something out very important. Those of you who did not really enjoy the Lewis dot structures, I got bad news for you. They're not going to go away. The first half of this set of lecture slides deal exclusively with Lewis dot structures. Beyond that, most of us are planning to take organic chemistry. If you're going to do organic chemistry down the road from this class, absolutely positively, the most important thing you will learn in this class is Lewis dot structures. Everything you do in organic chemistry is based on your ability to draw Lewis dot structures. So my advice to you is to get used to it and take the time to learn how to do Lewis dot structures if you did not in the last unit. Okay, so where we're going to go with our Lewis dot structures this time, though, is a discussion of the so-called molecular geometry. What we mean by molecular geometry is the shape of the molecule. Now, when we talk about the shape of the molecule, why is that of great importance? Well, particularly when you add the idea of the charge based on the electronegativity of the elements, the shape of the molecule becomes incredibly important in determining the long-range effect of how they look at each other or are influenced by each other. You see, what happens when charge is imbalanced in a molecule, it has pockets of positive and negative charge that are now electrostatically able to attract other molecules in a bulk sample. Now, this leads to a wide variety of their molecular properties, the point at which they boil, how much vapor pressure they exert above their liquid phase, the point at which they freeze, and on it goes, how soluble they are, whether they will dissolve in polar or nonpolar solvents. All these properties are examples of results of the bulk electrostatic attractions that molecules exert on one another. We call these properties intermolecular forces. In between molecules, the forces they exert on one another. Okay, so in conclusion there, to understand intermolecular force, we have to understand how charge is distributed over a molecule. To understand how charge is distributed over a molecule, we have to understand its shape. Another thing in biology where this becomes incredibly important, there's a lock and key model for the activity of binding and recepting molecules towards the activities that make us alive. Protein molecules, enzyme molecules, and these things are huge collections of atoms that have convoluted but very ordered structures. Very particularly shaped in a particular fashion. So essentially, they can be recognized by other biomolecules. And then when they bind together, they do such things as give us emotions, fears, make us sad, make us happy, make us feel pain. All these sorts of things that make us alive ultimately result from the way certain molecules bind to other molecules and trigger responses within a living system. Okay, so with all that behind us now, let's just go into some basic ideas about the shape of a molecule. Now remember, a molecule is a collection of atoms, and those atoms are made up of protons, neutrons, and electrons, and of course, the protons and neutrons constitute the nucleus. And the nucleus is by far and away the hugest part of the atom. So when we put atoms in combination, the vast majority of the bulk of the molecule is due to the nuclei. So when we're talking about molecular geometry, we're only going to be speaking about the location of the nuclei. So the nuclei are going to create for us sort of a atomic skeleton. Then we're going to spread over this atomic skeleton a derma of electrons. So a skin of electrons is spread over the skeleton. Well, also, the electrons, of course, are primary in holding the nuclei together. So the bonding is generated by the electrons, and other electrons are spread over the nuclei as well. Remember, we're only going to model the bonding of the nuclei based on the valence electrons, the outermost electrons of the atoms. There's plenty more electrons, of course, that each atom possesses, so we got to keep that in mind. But in any event, ultimately we're going to dictate or define the shape based on location of nuclei. So let's take simple diatomic molecules where you combine two nuclei. If you have two nuclei in combination, of course, you can draw a straight line between those 2 points of those nuclei. So all diatomics make what we would call a linear molecule. The only shape of a diatomic is what we will term linear, atoms in a straight line. But if you go to polyatomics other than 2 atoms, now the shape is going to be determined by how the electrons distribute around a central atom. Remember when we draw the formula, the empirical formula, for instance, for the molecule you see on the left, that is, of course, ammonia, but we would write its formula as NH3. Now, NH3, when we're drawing the structure of it, we put the N in the middle and surround it by 3 H's. So what we're going to do as we study geometry is we're going to take that central atom, have atoms connected to it, and then we will define the geometry relative to the central atom. So the geometry of NH3 is defined relative to N. Now that might seem prohibitively limiting because I can only do a molecule with one center. Well, that's not the case. Remember, we talked a little bit about organic nomenclature of their structures, and I said there was something called ethene. Well, let's start maybe with ethane. Ethane was CH3CH3, implying 2 CH3 units bound together. So what I do is I take the first CH3 unit, spread the H's around the C, stick a bond out from it, connect it to another CH3 unit, and spread the H's out around that C. So each individual point along a complex molecule can be broken down to what we will call a center around which we will determine the geometry. So you see the bottom molecule I'm showing here, CH3CCOH. There's a local geometry around each of the 3 C's, and there's a local geometry around the O, because those are the atoms that have others bonded to them. So there's various regions of bonding types that we see as the molecule gets more and more complex. I also want you to note in the ammonia and also in that other organic molecule shown at the bottom right that I've altered the appearance of some of the bonds. What we're trying to do is give perspective to the shape of the molecule because, of course, the paper is flat. And because the paper is flat, it looks like every molecule you would draw on it is 2-dimensional. And of course, there is the possibility that atoms stick into or out of the plane of the paper. So those new bonds that we have introduced on the ammonia and on the organic molecule at the bottom have wedge shapes to them that are attempting to indicate to you whether or not the bonds are lying on the plane of the paper. From now on, what we will claim is any thin line bond, like you see in the O2, is a bond lying straight right on the paper. You'll notice in the ammonia there is one bond of that type, and there are 2 wedgy looking bonds, and they have different appearance of wedge, and the idea of the different appearance of the wedge is that one of the bonds points towards you and one of them points behind the paper. Now, which one is which doesn't really matter, but at least we know one of them points out and one of them is behind the paper. The organic molecule on the bottom right has most of its bonds in the plane of the paper. So most of the molecule is what we would say is planar, flat. But you will notice the left C has 3 H's on it, one of them in the plane of the page. The other 2 are such that 1 H is sticking towards you and 1 H is going behind the paper. So please keep that in mind. That's going to be a very important aspect of how we are going to draw the bonds of these molecules. Okay, so now as we get into understanding and investigating and describing the nature of the arrangement of the shape of the atoms in a molecule, we're going to use an idea that is very routinely applied in chemistry, and that's called VSEPR theory. VSEPR is kind of not really a word. It's an acronym, VSEPR, and it stands for valence shell electron pair repulsion theory. Okay, now that sounds incredibly highfalutin and fancy and hard to understand. Valence shell electron pair repulsion theory. Well, let's look very closely at that name and parse it out into two-word sections, and we'll see that we should understand exactly what it means by doing so. Valence shell. The meaning of the first two words is we are only going to use the valence electrons on an atom. So for instance, oxygen has 8 electrons, but 2 of them are in the 1s level. Those are core electrons, and the remaining 6 are in the valence electrons, Those are the ones that we use in the Lewis dot structure. So we will only use valence electrons, bottom line. The next two words, electron pairs. Well, we talked about that as we bonded atoms together. The electrons always pair in bonds because you have to have the property that one is spinning up and one is spinning down. Then finally, repulsion theory. Guess what? Pairs of electrons are negatively charged entities that push each other apart. So when we draw the shape of the molecule, the bottom line is we're going to let the pairs of electrons push each other as far apart as they possibly can. And then that will help us decide what the shape of the molecule happens to look like when we are done putting the atoms out in space. Now then, let's give the rules for VSEPR or VSEPR theory. There are 3 rules that are fairly simple, really, after you get a little bit of practice with them. And these will govern, ultimately, the shape of molecules, whether they have a single center of bonding or multiple centers of bonding. First, the repulsive electron pairs on the central atom get as far apart as possible. Now, let's maybe add one more word into that one. The repulsive valence electron pairs. Let's make that clear. We're talking about valence electrons only. And then what you do is, of course, these electron pairs, in the attempts to complete their octet, are going to share electrons with external atoms. And so that creates what we call the chemical bond. If it's sharing with another atom of the same type, it's covalent. If it's sharing with another atom of a different type, it will have a different electronegativity, and if the bond's a little bit polar, we call that polar covalent. Now then a central atom will have a number of these pairs around it as it bonds outwardly. Now maybe it's not even totally bonding, but it has non-bonding pairs as well. But the point would be, no matter what kind of pairs they are, bonding or non-bonding, those pairs on the central atom get as far apart as they can. If the central atom possesses different hierarchies of bonding, meaning single, double, triple bonds or whatever, these bonds are treated as if they are really exactly the same and repel each other exactly the same. So if a central atom, say, has one double bond and 2 single bonds, or a central atom has one double bond and 1 single bond, we're not going to say that the double bond is more repulsive than the single bonds. The double bonds and single bonds repel exactly the same. Same thing would be true if it has 1 single bond and 1 triple bond. Now, why would we make a claim like that? It would seem like there's way more electrons, and of course the one with more electrons would be pushier. Well, keep in mind another concept from our last unit, and that concept was resonance. Remember, as we discussed in resonance theory, these single and double bonds are really not located constantly at a single point around the central atom. for instance, in SO3 sulfur trioxide, we demonstrated that all three oxygens bonded to the central sulfur can contribute a pair of electrons to the sulfur and double bond with the sulfur. All of them are equally likely because all the sulfur oxygen bonds are equal in length and all the sulfur oxygen bonds are equal in strength. So what we just claim as we're trying to draw it with Lewis-Strauss structures is that this double bond constantly hops between the three O's, and that gives us the so-called resonance. So now what we're claiming here, essentially in claim number 2, is that bonds that are resonance bonds are equal in repulsion. That's all that we're saying. Then finally, idea 3. If you're a non-bonding or lone pair of electrons, then you are pushier than a bond pair of electrons. Why? Because they're not so shielded by the positively charged nuclei when they're not involved in being shared between two nuclei. So the bottom line is, if you are non-bonding, you are pushier than a bonding type of electron pairs. Review the ideas of multiple bonds versus single bonds. Let's review the ideas of non-bonding or lone pairs versus bonding pairs. And what we see here is I have two structures. The one on the left is sulfur trioxide. Sulfur trioxide actually has a central sulfur bonded to three oxygens, as you see, and you should recognize that it exhibits resonance. I have drawn the double bond extended to the top oxygen, and it has two non-bonding pairs of electrons, but that double bond could also be distributed to the left oxygen or the right oxygen. All these bonds are the same length, all these bonds are the same strength. So what we would claim in this SO3 molecule is that the SO double bond is not more repulsive than the SO single bonds, so that that top bond is not pushing harder downward on the SO single bonds than any other bond would push on those. Now notice the S in the center has no non-bonding pairs of electrons, and those bond pairs literally get as far apart, and I'm trying to indicate actually the geometry of this by how far apart I am pushing the SO bonds from one another. Now also notice I've also drawn them with thin lines, and we talked a little bit about what the thin line implication was a couple slides back. The thin line means all these bonds are lying flat on the page. So this is a flat molecule where the bonds are getting as far apart as they can in a 360-degree total fashion around that central S. Now to the right we have the water molecule. Now the Lewis-Strauss structure of water is such that it has a single bond from the O to the H's, and there are two non-bonding pairs of electrons on the O. I'm trying to also indicate, cartoon style, the shape that a water molecule takes, which turns out to be a very important shape. The non-bonding pairs of electrons on the central O push the bond pairs of the H's away from being linear. If those non-bonding pairs were not there, the HH single bonds would be 180 degrees apart from one another. But the non-bonding pairs or lone pairs on the central atom are highly repulsive, and they end up pushing the bond pairs down to an angle less than 180 degrees. Now that we have some of the basic ideas behind us, let's start looking at the shapes of molecules. Now I'm going to tell you right now, there are 13 different shapes we're going to look at. And of course, as you know me, I'm going to require you to know pretty much everything there is to know about all of these shapes. So let's start with what we will call shape number 1. And shape number 1 is linear. And of course, what the word linear implies is that the atoms all lie in a straight line. Now, we already talked about the fact that a diatomic is always linear. Cl2, F2, O2, N2, linear. What we're talking about in this particular instance are a collection of more than two atoms yet all the atoms lie in a straight line. Now, I'm showing here the basic unit of linear molecules is AB2. Now, what we mean by AB2 is that the central atom is A, and it has two B's connected to it. Now, I want you to also note I could concatenate that together to make a more complex linear molecule. If I had AB2, 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 well, actually, that might not quite work like that. Sorry, that wouldn't work like that. Sorry. Let's scratch that. What I would have to do in order to make this work is remove one of the B's. That has to be done. Why? Because this AB2 unit has to be able to connect to another AB2 unit. If this AB2 unit was to connect to another AB2 unit, I would have to pop a B off of it. Then I would have AB connecting to AB. That could be linear. Now, if I was going to connect the third one, the central AB2 unit would have to have two B's popped off of it so that it could reach outward and connect to two other A's. So, three-center linear molecule with this notation would be AB, A, AB. Then it could be linear if I did something like that. Maybe rather than do more complex ones, let's leave that out. Let's do single center shapes. After we learn the single center shapes, I will come back and discuss with you multi-center linkage of the single center shapes. So again, let's maybe scratch all that time I just wasted, and let's talk only about single center geometry molecules. So in this particular instance then, if I'm going to have a linear molecule, it will have a formula AB2, and there are no non-bonding pairs of electron on A. That's what makes it linear. If there were non-bonding pairs of electrons, the bond pairs would be pushed apart from being straight out from one another. But because there are no non-bonding pairs on A, the AB bond on the left gets as far away from it as it can from the AB bond on the right. So the bonds push apart, push apart, push apart until they're 180 degrees apart, and that is the maximum distance with the minimum repulsion that those two can feel for one another. So linear molecules have a bond angle between the bonded atoms. The angle BAB is 180 degrees. This is a quantity I would expect that you could regurgitate to me if you were so asked. Look at a couple examples of linear molecules. We'll begin with silicon disulfide, SiS2. Silicon is in column 14, 4-dot Lewis dot structure. Sulfur, column 16, 6-dot Lewis dot structure. The simplest one to fix up is sulfur. Sulfur needs, of course, a complete octet. Sulfur needs two more electrons. Each sulfur gets the two more electrons from the central Si. So Si puts two into the sharing bond towards each sulfur. However, silicon has 4 valence electrons, needs 4 more. So rather than imbalance by getting 4 electrons from one or 3 from one and 1 from the other, of course what happens naturally is that each sulfur kicks 2 electrons into the silicon in the center towards it so it can complete its octet. So with dots, I show you the Lewis dot structure of the silicon disulfide, and then below that with lines, I show you the Lewis dot structure of silicon disulfide. Notice there are no lone pairs on the central Si. The bond pairs, whether they're single or double, push each other as far apart as possible. They push 180 degrees apart and stop. So SiS2 is linear. Now, as a matter of fact, this is of course, SiS2 is not such a common molecule, not nearly as common as CO2. That's the product of aerobic respiration, and it's also the reactant of plant photosynthesis. And so it's a very important system on this planet, and we're all very well aware CO2 is gas phase material. The reason CO2 can be gas phase is, of course, that is isovalent to SiS2. So, of course, CO2, which has a total of 16 valence electrons, just like SiS2 has a total of 16 valence electrons. The bond of the CO2 gets 180 degrees apart, and this is a very nonpolar arrangement of the C's compared to the O's. The O, of course, is more electronegative than the C, but we have an O pulling equally outward left and right, and CO2, of course, is very nonpolar, evidenced by it being a gas at normal temperatures. The non-stickiness of carbon dioxide molecules, even though they're relatively heavy as gas molecules go, they still can be a gas at normal temperatures because of the way charge is distributed between them. Now let's do a Lewis dot structure of the system NO2 plus 1. Now, I really don't know the name of this, what technically you should call this. If it was neutral, I would know how to name it, and it's not our typical polyatomic ion we've talked about before, but in any event, let's talk about the number of electrons it has. Notice N is in column 15, has 5 valence electrons. O is in column 16, 6 valence electrons. This totals up to a total of 12 plus 5 or 17 electrons, but because it's NO2 plus, you remove one of the valence electrons. And remember, as I talked with you about, you should remove the valence electron from the central atom, so I'm going to pull an electron away from N. And when I do so, notice that SiS2 and NO2 plus, and CO2 for that matter, are isovalent. They would have the exact same number of valence electrons for the cation NO2. So, of course, they're going to bond in exactly the same way as I show you in the picture on the right. Now, another example of a linear molecule that I show is HCN. The C in the center has 4 valence electrons. The H on the left needs 1 more, so the C gives 1 out towards the H, single bonding to that H. The N on the right has 5 valence electrons, needing 3 more. So the remaining 3 valence electrons on carbon are handed out to the N, making a triple bond with that carbon. Now, why is that the case? Because remember, C needs a total of 8 itself. It only had 4 to start with. So H shares 1 with it, N shares 3 with it. So HCN is a triple bond between the C and the N, while there's a single bond to the H. Now this single and triple bond push as far apart as they can, particularly because there's no lone pairs on the C. So the HCN bond is a triple bond. I'm sorry, is a 180-degree bond. Turn to the second of our 13 shapes. Shape number 2 is what I'm going to call a trigonal planar molecule. The name implies exactly how the atoms are arranged around the central atom. The general formula of a trigonal planar molecule will be AB3 as compared to the linear AB2. Once again, there are no non-bonding pairs of electrons on A. So there's 3 sets of bond pairs. And these 3 sets of bond pairs push each other apart as far as they can. So to get as far apart as they can, since there's 360 degrees all the way around, I'm going to spread these 3 collections of electrons as far apart as I can. So each will be 120 degrees from the other. Now, let's talk a little bit about how this would be possible. If the central atom has 3 things connected to it and has no non-bonding pairs of electrons, that means the central atom must possess a double bond. It must. Let's think about it. Let's say it's AB3, no lone pair on A, and all single bonds. That'd be 2 electrons from AB bond 1, 2 from AB bond 2, 2 from AB bond 3. That's only 6 electrons on the central atom. Doesn't work. What if I have 2 double bonds between A and B and 1 single bond? Remember, there are 4 electrons in a double bond, so that'd be 4, 4, 2. That'd be a total of 10 electrons. That doesn't work. Of course, 3 double bonds wouldn't work. That would be 12 electrons. That doesn't work on the central atom. What if I instead have a single bond, triple bond situation? Triple bonds are 6 electrons. 2 single bonds are 4 more electrons. That'd be 10 electrons on the central A. That don't work either. Okay, so the only way the central A can have no non-bonding pairs of electrons, yet have 3 bond pairs, and the bond pairs make it such that it has a complete octet. The only way to do that, 1 double bond to one B, 2 single bonds to the other 2 Bs. This, of course, leads to resonance. It doesn't matter which B does the double bonding. It's just an artifact that one of them must. So the double bond can hop between AB, 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 all the way around there so that all the bonds are the same length, all the bonds are the same strength. And remember, in Vesper theory, a double bond is not more repulsive than a single bond, and mainly that's because of resonance. So these 3 AB bonds get 120 degrees apart. Look at some examples of trigonal planar molecules. We'll begin with, instead of doing SO3, why don't we, just for fun, do OS3, oxygen trisulfide, which of course is possible. Okay, so of course S and O are each column 16 6-valence electron elements. So between them, of course, there are 6 electrons on each of the 3 sulfurs and the oxygen, so that makes 24 total valence electrons. If the O were only to just hand 2 outward to the S's, that would make the S's happy, yet the O is not. So one of the S's says, all right, I'll give a pair in. Now then, in nature, one S is not more likely to do so than the other 2, so there is resonance, or the double bond is literally allowed to hop from left to right, to left to right, to left to right, to top to left to right, to top to left to right in the OS3 molecule. So then these 3 equivalent bonds repel each other equally, and you get the structure that you see on the bottom right corner. Now in that picture, I'm drawing the dots with lines. I'm talking all dots with lines. I really prefer bonds with lines and dots for non-bonding pairs. That's pretty much conventional chemist notation. But I probably got lazy here. I remember I got to draw all this crap out. It takes me a while to do it, so I just did it this way for brevity. Now on the bottom left, I show a isovalent case to OS3, and that is the nitrate anion. So the polyatomic anion nitrate, of course, gains an electron from some external source, maybe a lithium, maybe calcium, maybe copper, who knows what. But to build the polyatomic anion, you must throw in an extra electron. So the central N begins with 5, but upon throwing another electron into it, it has 6 valence electrons, just like the O above. The 3 O's attached to it, of course, have 6 electrons, just like the 3 S's above. So there are 24 valence electrons in nitrate, just like there are 24 valence electrons in oxygen trisulfide. So the bond pairs in the nitrate polyatomic anion Vesper picture are going to distribute themselves exactly like the bond pairs in oxygen trisulfide. So nitrate is a trigonal planar anion as demonstrated in the picture. Now remember, another thing I want you to keep in mind. To draw the Lewis dot structure, ultimately I put the added electron onto the N and then allow it to bond outward to the 3 O's. Technically, that electron can go anywhere into the molecule. So what we do is we group the entire molecule in parentheses and put the total charge on the outside. That is good chemistry hygiene, and that's how these things should really be done if they're done correctly. Move to the third of our 13 shapes. This one I will call tetrahedral. A general tetrahedral molecule has the structure AB4, where A is in the middle, connected to 4 outward B's. Once again, there are no non-bonding pairs of electrons on the central A, so we have 4 bond pairs. Now, we should think about that, how that can be a possibility in a complete octet central A. Very simply, it has 4 bond pairs outwards, and it's completing its octet. All these bonds must be single bonds. So in an AB4 molecule of this type, the AB bonds are always single bonds. Okay, well, then let's think about how these bonds can distribute themselves in space. The easiest envisionment would be like putting it on paper and putting the 4 B's outward from the A's, and then they would be 90 degrees apart. So if I smush it on paper, I can kind of put the B's in a circle around the A, and then one B is 90 degrees or perpendicular to the next B. Well, that's fine, but I can actually repel the bond pairs a little further if I take advantage of the third dimension. Remember, the paper is flat, and we're only looking at the XY displacement of the B's. If I look at XYZ displacement of the B's, or 3-dimensional displacement of the B's, I can in actuality place them all 109 degrees apart. So the cartoons below that, I'm attempting to show that. Now I've got a shaded pyramid trying to attempt to show you that one of the B's would be coming towards me, and one of the B's would in actuality be going behind the paper to make it 3-dimensional. Now the picture on the right, the cartoon on the right, is really not a good cartoon in my estimation of how to draw this, because it does not show really clearly that I am which B's are sticking out of the page, which B's are on the page, because all the B bonds appear to be very, very similar. In any event, if you measure the AB or the BAB bond angle, there are 4 BAB bond angles that I'm looking at right there in my picture. 1, 2, 3, 4. There are 4 of these. Actually, there's more than 4. There's a BAB on the back side. There's a myriad of BAB bonds here in this picture. They are all 109.5 degrees apart. Now again, if it had only been a 2-dimensional molecule, then the BAB bonds would only be 90 degrees apart. So by taking advantage of the 3rd dimension of space, the AB4 molecule can get a little more distance between its bonding pairs. The simplest possible tetrahedral molecule would be methane. And of course, remember, methane is CH4, the central C with 4 electrons to share. And of course, each H wants to share 1 to make a single bond. So I would have 4 single bonds between C and H, no non-bonding pairs of electrons on C, and that would of course then make those bonds spread tetrahedrally apart. But let's look at maybe a little more interesting case. Let's look at the sulfate anion, SO4 minus 2. Now, again, sulfur and oxygen are both column 16 elements, both 6 valence electrons. I have 5 total elements there, and so I have, for the neutral atoms, 30 electrons. Because this is SO4 minus 2, I need to throw in 2 more electrons. I should draw the Lewis dot structure using 32 electrons. Now what I do in the cartoon below is I added 2 more dots into the mix, And as I told the recipe to do, I add the dots to the central atom. So I now just simply, this makes it seem, I think, pretty straightforward. The S really now has a complete octet when I put the 2 extra electrons onto it. Now, of course, where do those electrons come from? Those electrons would come from magnesium, manganese, whatever else that it is ionically bonding to. So the central S has its complete octet, and now conveniently the 4 O's can just slide right on to a pair of electrons distributed outward from that S, and that will complete the octet of all the 4 O's as well. Now, that leaves no non-bonding pairs on the central S. It's all bonding pairs between S and O. So these 4 sets of bond pairs start pushing each other apart. They could get 90 degrees apart if the thing stays planar, but the thing goes 3-dimensional, taking up the 3rd dimension of space as well, to allow the bonds to get 109.5 degrees from one another. So the cartoon I'm showing on the bottom is representing that. And how I do so is to introduce once again these hatched and solid triangular bonds. One of them is off the page out, one of them is off the page behind. Which is which, I don't care, but one is pointing towards you, one is going behind you. Now remember, the other idea is the thin bond. As we've used all along, now the implication of the thin bond is in the page. So 2 of the SO bonds are right on the page, and the other 2 are sticking out from the page. Look at some cases where the central A possesses some non-bonding pairs. So far, this linear, trigonal planar, and tetrahedral, there were no non-bonding pairs on that central A, so we could just push all the bonds as far apart as we wanted to. But now we have to alter things when you put non-bonding pairs on the A. Now the deal is this. The bulk of the nucleus is really overwhelming when determining the geometry. The geometry is solely determined from the location of the nuclei. Now, even though the electrons are doing the pushing, they're pushing the location of the nuclei. So we're going to monitor not, we're going to arrange the bond pairs and the lone pairs as far apart from each other as we can, but now then we're going to return to where the nuclei are in order to decide the actual shape. So, for instance, I'm showing here a central A that has a complete octet where it has a non-bonding pair of electrons and 2 bonding pairs. Well, these bonding pairs actually demonstrate resonance, that double bond B can hop between the right and the left B, and the non-bonding pair takes up a position that would have been reserved in the molecule above for a B. Now, if the non-bonding pair was equally repulsive to the bond pairs, then the angle of the connection between the 2 lower B's would remain at 120. But experimentally, what we find is if you begin with a molecule that kind of looks like it wants to be tetrahedral because it has 3 sets of electron pairs around it, yet one of those positions is not a bond pair, but it's a non-bond pair, that angle for the remaining 2 B's is always less than it would have been had there been a 3rd atom attached. This is invariably the case in all molecules that use this kind of bonding. So essentially what we've done is popped a B off of the structure, replaced that B with a pair of 2 dots, and really the shape of the electrons. Now, remember, the electrons around the A are still attempting to be trigonal planar. 3 pairs of electrons push about 120 degrees apart. But because one of those pairs of electrons is involved, 2 of them are involved in bonding, actually 6 total electrons are involved in bonding, and there's a non-bonding pair. Turns out that non-bonding pair is pushier. And so the angle between the bond pairs is going to be less than 120. Now, how much less? Well, we really can't quantify it exactly, but we can certainly say that the bond angle in a case like this will be less than 120. And I want you to recognize that and be able to state a case like that, as we will see going forward. I'll move to our fourth of the 14 shapes, and I'm going to call it a bent molecule. So like the linear one, a bent molecule is AB2. But previously our AB2 that was linear had no non-bonding pairs on A. In this particular instance, the central A has two B's bonded to it, yes, but it has a non-bonding or lone pair on the A, as well as the two B's attached to it. Now, before we go any further, let's think a little bit about how that it would be possible. A needs a complete octet. A has a non-bonding pair, so it has 6 remaining electrons that it needs. And if it's bonding to the B, those 6 electrons are distributed between the two B's. What that simply means is there's not 3 to one and 3 to the other. They go in pairs. So to get those 6 electrons distributed to those two B's, you must have a single bond to one B and a double bond to the other B. So anytime we're going to have one of these bent molecules, it's going to have an A with a lone pair, a single bond to one B, and a double bond to the other. And of course, what that would mean is when I have one of these bent molecules, it should always display resonance between the two B's that are bonded to the A. Now, if we just look at the 3 pairs around the central A, they would try to be about 120 degrees apart. But the non-bonding pair is pushier. So the 2 bond pairs get pushed away from being linear and pushed away even from being trigonal planar, so that now they're bent downward to less than 120. And I want you to recognize that. If I were to ask you what is the bond angle in a bent molecule, or what is the bond angle in an AB2 molecule with one lone pair on the A, after a little bit of thinking about it, you should come to the conclusion that there are 3 pairs on the A, but they would try to get trigonal planar to one another if there are 3 on it, but since one of them is non-bonding, it pushes more, so the remaining bond angle would be less than 120 after that pushiness. Look at an example of a bent molecule, and for that example, I'll take ozone. Ozone is a name that you have probably heard of, your mom and them have heard of. Ozone is an allotrope of oxygen. Allotrope is a collection of the same atoms just hooked together differently. So just like oxygen, ozone is made up of O atoms. However, this is 3 O atoms in ozone compared to 2 O atoms in oxygen. Just a few more things to say before we move on about the great importance of ozone. Of course, there's a lot of oxygen in the atmosphere, and very interestingly, when light from the sun strikes the Earth's atmosphere, at its outer edge, part of that light is absorbed. It turns out to be in the UV, and that absorption of light changes 3 O2 molecules into 2 O3. So there is a so-called ozone layer created at the outer edge of our atmosphere, where the ultraviolet light of a certain frequency strikes the atmosphere. That frequency of light stimulates O2s, as a matter of fact, 3 O2s, to convert into 2 O3s. Now, the interesting ramification of that is now that particular frequency of the UV radiation is removed from sunlight. So now as the sunlight streams down to Earth, certain components of the UV have never been here because they are absorbed by the ozone layer. So the implication there is that life for the past tens of thousands of years has been developing on Earth. And there are strict rules of the development of life, of course, as we're all well aware. And those rules are being played under the guidelines that this ozone has not been present as life has developed on this planet, because it's always been absorbed by the upper atmosphere as long as there have been critters roaming this Earth. Well, now humans have added such pollution to the atmosphere that floats up there and pokes holes in this ozone layer. And the problem then is that now this ozone is not present to absorb these certain UV frequencies, and now these UV frequencies are streaming down to the surface and impinging on all the critters on the surface. Well, come on, I'm going to explain to you very simply and very bluntly. Mother Nature plays its rules in a very systematic and rigid fashion. And if Mother Nature played the rules of development of life on this planet without the presence of that light involved in that evolution, then life has developed knowing that life has developed without that light in the mix. Now that we have added that light into the mix, it is causing problems, stimulating cells to go a little bit out of whack and a little crazy, generating cancer in not only humans but also other critters as well. So this imbalance we have created by destroying our ozone layer is really not a good thing, because, as I said, Mother Nature plays the rules by a certain set that have been used for millennia. All right, now I'll get off my soapbox there for a moment. Let's talk about building structure of Lewis-Dot form for ozone. I'm going to connect the O's in a line. I really can't say there's a central O. I put one O in the middle and put two O's outward. 3 O's have a total of 3 times 6, or 18 valence electrons to play with. I have to put 18 valence electrons together so that all atoms have a completed octet. Now the 2 outer O's, of course, need 2 more electrons. They get them from the central O. So 2 electrons are shared outward by the central O to the outer O's, but the central O still needs 2 electrons. It does not get one from each O. One of the O's says, I'll pony up 2 and double bond to the central O. So there's a double bond to one O outward and a single to the other. Now, of course, again, this creates the instance of resonance. Arbitrarily, I chose the right O to double bond and the left O to single bond. Equally likely, the left O could be double bonding and the right O single bonding. So there is resonance between these bonds. They are the same length, they are the same strength, and also in the ideas of Vesper, they are the same repulsion. So one of these will not push each other apart harder than the other will push apart. Now there are essentially on the central O 3 sets of pairs of electrons, 2 resonance bonds and a non-bond pair. These pairs get as far apart as they can, which would have been 120 degrees, but since one of them is a non-bond pair, it pushes a little harder so that the OOO bond angle that remains is less than 120 degrees. Now, again, we won't quantify it any more than that, but you should recognize that that bond is less than 120 degrees. For the 5th of our 13 shapes, I'm going to name this one like everybody else does, trigonal planar. A trigonal planar molecule has a formula AB3. Now that looks like, I'm sorry, I call this trigonal, it's trigonal pyramid, excuse me. A trigonal pyramid molecule. A trigonal pyramid molecule has formula AB3, just like a trigonal planar molecule. Now notice there's a slight differentiation in the statement of the name. trigonal planar, trigonal pyramid. If I say those two names, you need to be able to differentiate the meaning between them. Now they actually both are AB3. And the difference between them is that a trigonal planar has no non-bond pairs on A. A trigonal pyramid has one non-bond pair of electrons on the central A. The remaining are bond pairs. Okay, now let's talk a little bit about what those bonds must be like then. If this is trigonal pyramid that has one non-bond pair to 3 bond pairs, the A has 8 electrons around it. 2 of them are in the lone pair. That means 6 electrons remain, and it has 3 B's bonded to it. So there are 2 electrons shared between the A and the B in each case. So that means if you are a trigonal pyramid molecule, you have 1 lone pair and 3 single bonds. It's the only way that this is possible based on these arrangements. Okay, so again, these are things that we need to be thinking about as we go forward. Now, 1 non-bond pair, 3 bond pairs would be 4 total pairs of electrons on the central A. Before we saw that 4 pairs were tetrahedral. They got as far apart as they could by using the 3rd dimension of space and pushing 109.5. But since one of these is a non-bond pair, it's pushier. So the 3 remaining bonds, which would have been 109.5 had the 4th location had a B, will now be pushed so that they are tighter bonds than they were before. So the 3 remaining bonds are pushed to angles less than 109.5. Now these 3 remaining bond angles are not flat, just like tetrahedral molecules. They are 3-dimensional. The cartoon of probably the most celebrated trigonal pyramid molecule. That would be ammonia. Of course, ammonia is NH3. The central N is column 15, 5 valence electrons. The 3 hydrogens single bond to it, and so that gives it its complete octet. So it has 3 single bonds outward to the H's and 1 non-bonding lone pair of electrons. So as the cartoon is trying to show, 3 bond pairs, actually we'll start with all 4 electron pairs. They would push each other and repel to be tetrahedral. Now I pop an H off, if you like to think of it that way, off the top. Now, as a matter of fact, if you think about it, ammonium NH4 plus would be perfectly tetrahedral, but now NH3 has essentially removed one of the H's from the top and left it a lone pair. And so I have 3 bond pairs which remain 3-dimensional, but instead of being angles of 109.5 degrees, had they been, if it was a perfect tetrahedron, the non-bonding pair is pushier and shoves the bonding pairs, the 3 bonding pairs, to a little bit tighter than they would have been if that had been an H up there. Trigonal pyramid example. Let's take ICl3 plus 2. Weird molecule. Does it really exist? I don't know, but we can certainly draw its Lewis dot structure. Iodine and chlorine are both halogens in column 17. Iodine and chlorine both have 7 valence electrons. Neutral ICl3 would have 4 times 7, which would be 28 electrons. But now I'm going to remove 2. I need to build this structure with 26 electrons. Now, of course, each Cl wants, okay, maybe start at the beginning. I is the central atom. Remember what I say, the ease of drawing these is to remove the 2 electrons from the central atom. So I'm going to have 5 electrons remaining after removing 2 from the I. Each Cl, well, of course, the I needs 3 more electrons. It will get 1 each from each of the Cl's. The Cl's each need 1 electron. They will get one each from the I. So there will be 3 single bonds outward to the CLs and one remaining non-bonding pair of electrons on I. So the Lewis dot structure with dots is shown in the middle of the picture. Now at the bottom, I'm showing the VSEPR representation of the geometry. First of all, remember, as I've talked about with you several times now, I bracket it because it's charged, put the charge on the outside, indicating that I did it by taking the electrons off the I. They could have been taken from anywhere. Then, it would be tetrahedral if the non-bonding pair of electrons was replaced with a bond pair, but I still draw the shape as if it's tetrahedral. Now, a lot of people put a line connecting to the dots for the dots at the top of the I to show the kind of tetrahedral look of it. I'm doing something that many of us prefer to do, though. I'm just putting that position of the tetrahedral that should be vertical on the page as just a pair of dots on top of the I. Then the 3 remaining lines of the tetrahedron, I'm drawing where they should conventionally go. Now remember, the implication as I'm showing those thickened triangular bonds is that they are not on the paper. The thin ICL bond is on the page, then there's a solid triangular one and a hatched triangular one of which is coming out, one of which is going behind the page. This is 3-dimensional, and if you connected those sides with solid faces, it would be a triangular-based pyramid, or what we call a trigonal pyramid molecule. On to shape 6 of 13, and this is one I'm going to call really bent. Now I don't think this is what the book calls it. It calls it bent 2 or just bent, I don't know, but I'm going with really bent, and I'm calling it really bent to distinguish from bent. Now remember what bent was it was a tetrahedral based molecule where you pop one of the B's off and the remaining 2 B's are bent over to less than 120. Well, the really bent is also starts out the same as being AB2. It's like a bent molecule. Now, as a matter of fact, this is our third AB2. We saw an AB2 which was linear. If there are no non-bonding pairs of electrons on A, we have an AB2 which is bent. If there is one non-bonding pair of electrons on the central A, now I will have a really bent molecule of the form AB2 when there are 2 non-bonding pairs of electrons on the central A. There are bonds to the A's. Now remember, 2 non-bonding pairs is a total of 4 electrons, and the electron is bonding to 2 B's. That means it's sharing 2 electrons each with the B's. If you are a really bent molecule, the bonds you form must be single bonds. They can't be double bonds, or the central atom won't have a complete octet around it. Okay, so 2 non-bonding pairs, 2 bonding pairs. If these were all bond pairs, I'd have 4 pairs of electrons. It'd be tetrahedral. So again, the premise is this starts out attempting to be tetrahedral, just like the bent. This starts out trying to be tetrahedral, just like we saw previously in the trigonal pyramid. But now I got 2 non-bonding pairs taking up sites on the tetrahedral. So this remaining ABA or BAB bond would try to be 109.5, but because if all the pairs were B's, but because there are a couple non-bonding pairs there, it's pushier on the bond pair. So the BAB bond pair gets pushed to an angle less than 109.5. This is why I call it really bent. In the bent molecule, it's based on trigonal planar starting point, and the non-bond pair pushes the bond pair to less than 120. Here I got 2 pushy bonds taking up sites from a tetrahedral. So now we're pushing a tetrahedral to a smaller angle, so it's pushing to an angle less than 109.5. And I would expect that you could recognize that based on the fact that this is based from a tetrahedral, whereas in the trigonal planar case, the AB2 was based from a 120-degree angle distribution. Now, one more thing to say, maybe this is a little bit weird, that the really bent molecule is actually two-dimensional. Now, a trigonal pyramid, which is based on tetrahedron, is three-dimensional. A tetrahedron, of course, is three-dimensional. But now this really bent molecule, which starts out as being from a tetrahedron, which is three-dimensional, has atoms that can be placed in a plane. And quite simply, what we can think of is that we can put the dots in the positions on the tetrahedron, one out of the plane, one behind the plane of the paper. And the remaining two B's can be on the page with the A. In any event, in geometry, the rule is 3 points define a plane. 2 points define a line, 3 points define a plane. A two-dimensional surface needs to be defined by 3 points. A, B, B is 3 points. So those 3 points can always be in a plane. So this molecule derived from a three-dimensional molecule is itself planar. The most celebrated of all really bent molecules, which would be water. The central atom O has 6 valence electrons, and it will share 2 of those outward with each of 2 hydrogens, single bonding to 2 hydrogens. Remember, hydrogen does not want a complete octet. It only needs 2 electrons around it. So I have single bonds to the H's for 2 of the valence electrons of O. There are 4 valence electrons remaining. Those constitute 2 non-bonding pairs of electrons on the O. So now I have essentially 4 pairs of electrons around the O. Those 4 would arrange tetrahedral had they all been H's. So as a matter of fact, I could make a molecule OH4 plus 2, and it would be tetrahedral with arrangement around the central O. But now what happens is that 2 non-bonding pairs take up 2 of the positions on the tetrahedron. Now I'm showing them as if they were the positions in the plane because I'm using the thin line. But let's consider that I put them on the hatched bonds, which of course means H coming out and H going behind. And then put the H's on the lines with the thin bonds. That would show you that H2O is planar, and of course water molecules are planar. Now the way I'm drawing the picture, though, it appears as if it is non-planar because I have an H sticking out, an H going behind, and an O on the paper. Again, what I can do is rotate my coordinate system and have all the H's on the page and put the dots coming out and behind, and that would kind of show you that it is planar. Now then on the right, I show another cartoon that I stole from the book, showing the bond pairs that are pushed a little bit greater. Notice how it's showing the lone pairs to be in like greater lobes than the green bond pairs, so that I'm trying to emphasize the push from the lone pairs onto the bond pair. And if that had all been H's, all the angles would be 109.5. But because of the lone pairs, the bond angle between the H's and the O is less than 109.5, is how I want you to categorize that. Well, we've looked at 6 structures so far, and I promised you that we were going to review 13 structures total. To introduce the remaining 7 structures, we have to first discuss what we will call the hypervalent case. What we mean by the hypervalent case is when the central atom has greater than an octet of electrons around it. Now, so far, let's review the idea of the octet. That's when you have a main group element which has available S and P electrons. Recall from our previous unit, 2 electrons can occupy the s, 6 electrons can occupy the p, so that's a total of 8 electrons occupying the sp available orbitals. When atoms fill this up, they would have a so-called complete octet of electrons in this sp valence set. But what I want to remind you is that also on these valence levels, there can be vacant d orbitals. Remember, beginning on level 3, d orbitals become available. So a level 3 atom such as sulfur, which has a 3s and a 3p that it can occupy with electrons, just like oxygen had a 2s and a 2p. Well, now, in addition, on this same energy level, sulfur has this 3s and 3p to occupy, but it also has equal level 3d orbitals that have the possibility of getting involved and being populated. So hypervalency will result from electrons going beyond an 8 electron central atom because of the involvement of d orbitals in the bonding situation. We will only, for our simplicity, look at cases where we have 10 electrons around the central atom or where we have 12 electrons around the central atom. So that would be involving, in one case, maybe a single d orbital to occupy 2 more electrons above the complete octet, or in the other case, using 2 d orbitals to have 12 electrons around, 2 in the s, 6 in the p, 4 in d's. So this seems a little bit bizarre, but there are many cases in nature where these are seen to occur. Now, one of the things we will do in our hypervalent cases, just to keep our sanity such that we're not making it too crazy, is that we will only use single bonds for the hypervalent cases. So in the case where there's going to be 10 electrons around the central atom, there will be up to 5 single bonds on the central atom. In the case where there's 12 electrons on the central atom, and again, that's 3 p's involved, 1 s involved, and 2 d's involved to give a total of 6 orbitals that can hold 12 electrons. When we do that, there will be a total of 6 single bonds outward from the central A to the bonding B's. Now, what we will do with these extended amount of bond pairs is allow them to push and pull each other so that they will spread as far apart as possible. For our 7th shape, we'll start these hypervalent cases. The first will be what I call a trigonal bipyramid. Now look, I didn't do this and I didn't cause this mess, meaning we have something we call trigonal planar, we have something we call trigonal pyramid, now we have something we call trigonal bipyramid. This is standard chemistry discussion, so we're just going with the names that everybody across the nation calls these, and the name kind of says what it is. A trigonal pyramid, you'll remember, was a triangularly based pyramid shape. A trigonal bipyramid is essentially we're going to take 2 triangular pyramids and slap their bases together to make this trigonal pyramid molecule. Now, a trigonal pyramid molecule has the general shape or formula AB5. And just thinking about bonding, we should immediately understand that the central A is hypervalent. How do we know that? Because if it has 5 single bonds at minimum, 5 single bonds to B is 5 shared pairs of electrons with B, that's 10 electrons around the central A. So there's no lone pairs on the A and 5 bond pairs around the A, 10 valence electrons, hypervalent. Now, how are we going to describe this shape? Well, I'm just going to, the name says it all. It is what we call trigonal bipyramid, which consists of an equilateral triangle in the middle by 3 of the B's, and those equilateral triangle in the center has 120-degree bond angles for the B's. Now I put perpendicular to that plane of B's, I put a B above and a B below. And this will be a 3-dimensional molecule that I will show a picture of on the next slide. I want you to be able to draw the picture is shown here in black. Notice I have an A in the middle and I put a triangle of B's around it, one with a thin bond, 2 hatched and solid triangular bonds, and of course the implication is those are coming at you and going behind you. Then above that triangular plane of 3 B's in the middle, there's a perpendicular B above and a perpendicular B below. Now the B's in the triangular plane in the middle are all 120 degrees apart, as if that's a trigonal planar part of the molecule. Then above that and below that, 90 degrees from that plane above and below, is a B sticking on both ends. Now, of course, those 2 B's would be 180 degrees from one another. Now, when structures such as this are used in organic or advanced inorganic chemistry, we differentiate the names of the positions as being either equatorial or axial. Equatorial positions are the ones around the middle. Kind of like if you look at the Earth, we have the equator of the Earth, then the 3 B's in the middle are around the equator of the molecule. Then we have the polar ones at the top and the bottom, which are, maybe that would have been a better name, but they decided to use the name axial. So the axial positions are above and below the triangle, and the 3 in the triangle are known as the equatorial positions. Now, if we were to make each face, if we connected 3 B's together to make a collection of 6 faces for this molecule, then it would look like a triangular pyramid above and a triangular pyramid below with the triangle in the middle. So this is the nature of the name trigonal bipyramid. Let's look at a couple of examples. Let's begin with AsCl5, which of course I would name as arsenic pentachloride. The arsenic is in the center, bonded to 5 chlorines outward. The chlorines all need a single electron because they have 7 in their valence level. So they will single bond to the arsenic. Notice conveniently the arsenic has 5 electrons itself, so it will share 1 outward to each chlorine. The chlorine will share 1 inward to the arsenic, so it will form 5 single bonds to the arsenic in the middle. These bonds get as far apart as they can. They can't be linear, they can't be trigonal planar, they can't be tetrahedral, because there's 5 of them around it. They will get trigonal bipyramid. There are no non-bonding pairs of electrons left on the central arsenic after sharing 5 electrons outward. So I will arrange them around the arsenic as you see in the picture at the bottom. 3 of the chlorines in a central 123 degrees, if you like, trigonal planar arrangement in the middle. Those are the so-called equatorial chlorines. Then 1 above and below the plane with 2 axial chlorines. Notice all electrons are represented in the picture. There's 35 plus 5, there's 40 total electrons. Each bond pair is 2. Each non-bond pair on each chlorine is 2. So there's a total of 40 electrons represented in the picture when you draw it correctly. More example of a trigonal pyramid, trigonal bipyramid molecule. That would be BrH5 plus 2. Now, of course, the central Br is where I'm going to remove the 2 electrons. Originally, Br has 7 valence electrons. I remove 2. It now has 5 valence electrons, and it has 5 singly bonded H's attached to it. So there are 10 pairs of electrons around the central bromine. So there are 5 bond pairs connecting the central bromine. I put 3 of them in an equilateral triangle at the equatorial positions. Notice 1 thin H bond on that equatorial, 1 triangle solid and 1 triangle hatched, indicating 1 H coming toward me, 1 going behind me. Then I have an H above the plane with a thin bond, indicating it's lying on the paper. H going below the page with a thin bond, it's lying on the paper. So 3 of the H's and the Br are on the page. 1 H is pointing towards me, 1 H is going behind me. Then, according to my conventions that I'm supposed to adhere to, I contain the entire thing in parentheses, put the total charge on the outside to correctly exhibit the picture of this trigonal bipyramid molecule.